Hi everyone. So today I'm going to provide you with a geometric proof of the theory of special relativity. Special relativity is a theory developed by Albert Einstein in 1905 during his memorabilis year. Basically, the main finding, he revolutionizes our idea of space and time as from being absolute and unchanging quantities to being, let's say, variable, variables in our in our physical reality, which can be different according to different observer. And so the main thing that we are going to prove is that time can be different from me and from you. If that's a big if I am moving relatively to you at a very, very high speed. Okay, close to the speed of light, even a little bit before, but huge time dilation happen when one of the two observers is moving at a speed very, very big. Okay, now we are going to start with a Gedanken experiment, which is what Einstein taught, called the thought experiment, the thinking experiment. So experiment that you do with your mind. This is not very hard to imagine because you just need to imagine that there is an observer which is on a train. Okay, is our train, and these are wheels of the train, which does not look anymore a train, it looks a track. So this is observer, which has a very elongated body apparently, and this is observer A. What we are going to do is that observer A, or actually let's even declare first observer B outside the train. But okay, so basically the experiment will be we are ejecting a beam of light from here, inside the train, from the floor to the ceiling, onto a mirror. Okay, so the beam of light gets reflected. This, just to give a measure, is the distance d from floor to ceiling. And basically what we want to show is that, okay, basically the experiment consists like this. A is within the train. So A is moving very, very fast at a speed which is v, or speed v. Let's assume it is very, very high. What basically A is going to see is just, let's imagine like this. Let's imagine this is the beam of light. You will just see this. Okay? A vertical beam of light going from floor to ceiling. And what A will do is that it will take the time of this beam of light going from floor to ceiling, and it will say, okay, let's see how much time it takes for the beam of light to go from floor to ceiling. And it says, beam of light starts from the floor, take the time, sees the time, beam of light reaches the ceiling, it takes the time. And A records this time to be t. Okay, so A observes time t. Time t on the train. Okay, so A observes time t on the train moving at a very high speed, speed v. What B will see? Now, let's imagine that, how do you say, this is sort of easy to understand. Why? Because if you're on an airplane and you're moving very, very fast, and if you take something and you throw it in air, okay, that is not going to move any other way. It is just going to have a vertical, say, motion. And I don't know if it is correct, but it will have a vertical trajectory. Why? Because that follows from Einstein, let's say, definition of inertial frame of reference. Okay, within an inertial frame of reference, so a frame of reference respect to which, let's say, we are not accelerating, there is, let's say, all the laws of physics are the same. So every experiment must yield the same outcome. Okay, and what B will see? Okay, now I want you to think about the fact that if the train is moving, the beam of light will start. Now I will draw it, let's say, yes, I will draw it pretty much like this. Now imagine this train is moving. Okay, what will here there is observer B. What will B see? B, again, imagine this train is moving. B will see that the beam of light here starts being ejected, and from here it takes a diagonal path onto the mirror and back down to the lamp, to the source of light. Why? Now I ask you, if I am moving relatively to you, and I am on a train, and a beam of light gets ejected and come back, the path the beam of light will have will pretty much resemble something like this. Oh, you see why? Because I am moving. The beam of light is moving within a moving train. Let's put it this way. Okay, so by the time the beam of light here gets ejected and reaches the mirror, this train will have moved, and so it will have traveled a certain distance, not only vertically but even horizontally. So this is why the beam of light has a diagonal trajectory. Okay, so before going further, we need to state two crucial assumptions, which are not totally unjustified, and is that c, which is the speed of light, is which is 299,792, I think, yes, kilometers a second. It is very, very high. This speed is constant. What does it mean? It means that if I am standing still, right now, I am observing the speed of light to be this value. But now I start on a motion, and I am traveling at 200 kilometers per second. I will record, if I eject a beam of light, I record the speed, I will record the exact same speed. The speed of light is constant in every reference frame. The second assumption we are making is that nothing can travel faster than the speed of light. This is a consequence from Einstein's theory of special relativity. So, stated mathematically, which may, I don't know, it may piss some physicists off, but let's say that for all v, so for all velocities which are allowed, v is less than c. I hope you can see, but I just said v is less than c. So the speed of light is literally the upper bound, the upper limit for all velocities available. Okay, so we can come back to the trajectory that the light takes for the observer B, and so B will see this triangular shaped trajectory. So we draw it more nicely, and okay. So first thing is the trajectory the beam of light will take for observer B. But for observer A, we said it's only going to be a very simple vertical trajectory. What that is going to be? We know that this is distance. So this is literally the vertical distance that the beam of light has been traveling. We know the speed, which is c. We know the time, which is t. And also, sorry, I didn't mention it, but B observe. Again, imagine this is the beam of light, starts the clock, comes back to the mirror and goes back, stops the clock. Okay, so B observe time t prime. Okay, t prime is the time we observe of the train at rest relatively to the beam of light which is in motion. Okay, let's come back to the trajectory the beam of light takes as seen from observer A. What did we say? We said that it's just vertical. Again, go on a plane, go on a train, throw your AirPods, your rock, wherever you see, wherever you want, a beam of light, it will just go vertical. Okay, because you are at rest compared to the beam of light. So what we will have is that we usually have the relation that speed is equal to distance over time. Am I right? Yes, I think so. So c usually is distance over time. D is our distance here, and time is the time A records. So equally, if and only if, we can write distance t as c times t. Okay? Let's keep this for now. Very, very important. Okay. Again, here, distance traveled from the of the beam of light from the beam of light seen by observer B. So we start here. The beam starts here and travels this distance, which we'll call just for the sake of giving it a name. It's not important how we call it. We will call it d prime. D prime, by this, let's say, not the same relation, but the same, how do you say, the same concept, let's call it this way, but the same formulation, will be equal to c, because the beam of light has always the same speed, times d prime, right? Oh yes, because this is the time taken from observer B, that observer B observes. Okay, this is the time taken that observer A has observed. So a time going vertically from here to here. Instead, this distance is traveled as seen from observer B. So from here to here in time t prime. And so this is indeed the distance traveled, which is just c t prime. What is this? Of course, this you should know what is it. This is just d, our distance. Because let's imagine this as our train. Okay, this is how you should see it. This is our the trajectory that it takes within the train. So this is just the distance, the height of the train from floor to ceiling. And what is this? You may say, it's a distance within the train. No, you have to imagine again, this train is moving. So what is this distance here? From here to here. This distance, which again, for the sake of giving it a name, it's not important the name we give it to it, we will call it d double prime, is equal to the path, is the distance that the train has traveled in time t prime. So what is it going to be? By this same equality, this will be equal to dt. But why not c? Because this is the distance traveled by the train. This is the distance traveled by the light. So they have intrinsically two different velocities. Okay, the beam of light has velocity c, and it travels, t prime, of course, and it travels time t, and it travels distance d prime. The train travels distance d double prime at velocity v in time t prime, always the same time. So v t prime. Okay, this is very nice. This is very nice to see. And now we say, okay, wait a second. This is a triangular. This is a, how do you call it? A right triangle. Sorry, I forgot the name. This is a right triangle. We can apply Pythagorean theorem, and that's where the geometry kicks in. So we can start from here and we can rewrite. Okay, this is just followed by geometry. Okay. Hypotenuse? What is the hypotenuse? The hypotenuse is just given by the sum of the square of the two cathetus, I and D. That's just what we wrote here. Okay, but now we know one thing. We know that D, this distance here, wait a second, this distance here is equal to C times T. Let's try to substitute and see what comes out. Sorry, this is C squared. C, we substitute C times T squared plus Here we rewrite the same squared. Okay, what do we do now? Now we have to rearrange in one way or another. How do we rearrange? We bring to this side, we write ct prime squared, and we bring to this side, well actually let me write it out completely, so c squared and t prime squared minus this term here. Why? Shut up, it's gonna be clear later. Again, we write it out completely, so v t prime squared equal to, and this is just rewriting c squared t squared. And now we are going here